Okay, so are there any questions about what we did in the first hour? Okay, so you have to distinguish, in the case of quark-gluon plasma, you have to distinguish between the total density of particles and the conserved particle density. So the total density of particles, that's the density of quarks plus antiquarks plus gluons, and none of these numbers are conserved because quark-antiquark pairs can turn into gluons, and gluon can turn into more gluons, and in fewer gluons they can fuse and branch. And so none of these numbers is conserved. What is conserved is the difference between the number of quarks and antiquarks. That's the baryon charge. But the baryon charge density is not the relevant density in this case. What's the relevant density is the total density of scatterers. So what I wrote as n is really the total particle density, not necessarily the conserved particle density. That distinction will remain important as I move on. Yeah, so I will comment on that. Other questions? All right. So if you, in a somewhat simplified way, if you remember what we did, is that we can use the eta over S, the ratio, the specific shear viscosity, as a criterion to distinguish between gas and liquid behavior for massless particle systems. Eta over S large is gas, eta over S small is liquid. And the validity of hydrodynamics does not just depend on eta over S, but it depends on a product of eta over S and the expansion rate or other quantities that are related to the expansion rate, the velocity shear in a plasma, gradients of the chemical potential, gradients of the energy density, they all can replace that theta over T. So there is a product of the specific shear viscosity with that hydrodynamic length scale, with that inverse hydrodynamic length scale in proper unitless fashion that controls the validity of hydrodynamics. So as I said, I will now, for the next hour or so, I will pretend that we have a system that can be simultaneously described by the Boltzmann equation, so it has large eta over S, and by hydrodynamics, so it has a small Knudsen number, a small product of eta over S with the expansion rate, so it's a slowly expanding system. So let me start with deriving the equations of motion of ideal fluid dynamics. So the first thing I do is that for any observable, for any momentum-dependent observer, I define the expectation value with a distribution function as an integral over momentum of this observable with the distribution function. Yeah? So this quantity here is a function of x, because I'm integrating just over p. And this integral p is a shorthand notation for 1 over 2 pi cubed, which is really 1 over 2 pi h bar cubed, and 2 pi h bar is h, so this is 1 over the Planck constant cubed, what's standing here, times an integral over d3p over e, our Lorentz invariant momentum space integration measure that we derived yesterday, times O of p, f of x and p. So introducing this average with the distribution function is going to simplify the expressions very dramatically. So if I look at particle current, J mu of x, it's defined in kinetic theory as a momentum integral of p mu with f of x and p. So it's the average momentum of the particles in the distribution f of x and p. So it will just be p mu in this notation. And the energy momentum tensor T mu nu of x, which is an integral of p mu p nu f of x and p in Boltzmann theory, that will just be the expectation value of p mu according to this notation. Now now is a point where I should really distinguish between just particle current of a given particle species, such as the quarks, or the gluons, or the antiquarks, and a conserved current. And so in the strong interactions, we have a conserved current. At least one important conserved current is the baryon number current. There is, of course, also the electric charge current, which is conserved, because that's what quantum electrodynamics tells us. And there is also, if you take into account only strong interactions but no weak interactions, there is also a strange current that is conserved. The net number of strange quarks minus strange antiquarks is separately conserved from the baryon number, because the only way to destroy strange quarks and turn them into non-strange quarks is by weak interactions. But important for phenomenology is baryon number conservation. The others are not so important unless you get into a detailed discussion of the final chemical composition of, for example, looking at the kaon to pion ratio. Then you have to worry about strange currents. So the baryon number current is J mu B, which I get by taking my individual currents J mu I, and I'm summing I for quark, antiquark, and gluon, and each one of these guys I multiply with the baryon number Bi. So if I take a quark, it has a baryon number plus 1/3. If I have an antiquark, it has a baryon number minus 1/3. And if I gluon, it doesn't have any baryon number. Yeah? So this is 1/3 times J mu quark minus J mu antiquark. And so I can write this as a sum over I, Bi, P mu I. And the energy momentum tensor, the total energy momentum tensor, is again a sum over quarks, antiquarks, and gluons, T mu nu I. So it's a sum over I of P mu I. So if in a quark-gluon plasma, I really should always think about these three components: the quarks, the antiquarks, and the gluons. And then if you want to become more sophisticated and also worry about charge and strangeness, you should have the up quarks, the down quarks, the strange quarks, the charm quarks, all of the different quarks separately. I'm not going to do that because I will never end writing my equations, so I will pretend that there is just one particle species in the system, and you can do the generalization to the actual composition on your own. It's really easy. So if you assume local equilibrium, which means that you assume that your distribution function f of x and p takes the following form. It's an isotropic function of x, an isotropic function of p. I indicate that by an index ISO. And what I mean by that is it's a function that depends only on p dot u of x minus mu of x over t of x. It depends on this combination of parameters, where p is the form momentum of the particles, u is the form velocity of the liquid at the point x, mu is the chemical potential of that particle species that I'm looking at, and T is the temperature of my local equilibrium state at that position x. So if I take for the distribution function a function that depends only on this combination of parameters, then I call that if I assume local momentum isotropy. Actually, I'm not assuming equilibrium, so I should be careful. Momentum isotropy. Then I call that locally momentum isotropic. Why? Because P dot u of x goes in the local rest frame what's the local rest frame? The local rest frame is that reference frame in which u mu becomes, in the local rest frame, becomes 1, 0, 0. In other words, in which there is it's the frame in which there is no 3 velocity of the fluid anymore, in which I move with the fluid, and that means that the flow 4 velocity, which is normalized to unity, has a 1 in the time direction and 0 in the spatial direction. And then, of course, this product here just becomes E. And the energy in the local rest frame for on-shell particles is square root of m squared plus p squared in the local rest frame. And p squared is an isotropic function of momentum. Yeah, so that's why I call this an isotropic, locally isotropic distribution. P dot u is locally isotropic. Now, in local equilibrium, this is any function f equilibrium, where if I use this parameter, this u dot p, p dot u of x minus mu of x over t of x, if I just call that zeta, if this function becomes an exponential function, 1 over e to the zeta plus a, where a equals plus 1 corresponds to fermions, a equals minus 1 corresponds to bosons, and a equals 0 corresponds to Boltzmann particles, classical statistics. So for plus 1, this is the Fermi distribution. For minus 1, this is the Bose distribution. And for Boltzmann particles, it's just e to the minus of that argument. That's the Boltzmann distribution. So local equilibrium is a stronger assumption than local isotropy. Local isotropy just means that it's a function just of this variable. Local equilibrium means that this functional dependence is exponential. It's this one. Now, if we just assume this, we don't have to assume this. If we just assume this, then you can show that J mu takes its ideal fluid form, which is just n times u mu, and that T mu nu takes its ideal fluid form, which is just epsilon times u mu, u nu minus p times delta mu nu, where delta mu nu is g mu nu minus u nu. How can I argue that? Well, if you look at this function here, it's a scalar function, but it has a parameter in there that is a vector, and that's this flow velocity. This flow velocity is contracted with the momentum 4 vector to a scalar, so that this becomes a scalar function. But just like the chemical potential and temperature are parameters of this function, these are two scalar parameters, there is one parameter in there that's a vector. So when I integrate over the momentum, this vector here will generate possible tensor structures for the integral. So if you calculate the expectation of p mu, this has to come out as a 4 vector. But since I'm integrating over p, that 4 vector cannot be p, because p has been integrated over. So what is the 4 vector that the results, that integral, can depend on? The only parameter that has vector structure in the integral is that u. So that means that the integral of this integral has to be proportional to u. And the proportionality constant we call the particle density. That is the particle density in the local rest frame. Similarly, when you look at this object here, this is a symmetric tensor of rank 2. What kind of symmetric tensors of rank 2 can you generate from momentum integrals of this function? Well, there is always the metric tensor. It's a symmetric tensor of rank 2, which comes for free if you live in space-time. But because I have this vector parameter u in the distribution function, I can also generate tensors using that u. And one symmetric tensor that I can form is u mu, u nu. That's a symmetric tensor constructed for mu. And that's then everything, because if I have only g mu nu and the vector u, there are no other combinations that are symmetric and that have tensor structure that I can construct from that. And that means that T mu nu must be of the form A time, so in equilibrium, or in local isotropy. For local isotropy, it must be of the form A times u mu u nu plus B times g mu nu. And what I have done here is I have split the tensor, rearranged the tensor in a different way. I have kept the u mu u nu, and this is nice because in the local rest frame, u mu has only a time component. So in the local rest frame, this becomes the T00 component. And the T00 component, I know from general considerations, is the energy density. So the thing that multiplies the u mu nu is the energy density. And instead of using g mu nu, I'm then using g mu nu minus u mu nu, because if you go in the local rest frame, this takes out from g mu nu the temporal component. It takes out the T00 component, so it leaves only the spatial component. So this is the spatial projector in the local rest frame. And this here is the temporal projector in the local rest frame. And so by rearranging A and B in this form, I get a separation of T mu nu into its temporal components and its spatial components. And the spatial components I call pressure. Yeah. Why would I assume what? The current. Not in ideal fluid dynamics. In ideal, so if you have a distribution function which is locally isotropic, you don't get a distribution current, because this argument tells me that this has to be a 4-vector, and if the distribution function is given by this form, the only 4-vector that I can construct it from is u mu. There is nothing else. So you can only get a diffusion current if you violate this assumption that I make here. So if you have to violate local momentum isotropy in order to get a diffusion current. Okay? You're right, yeah? In viscous hydrodynamics we have diffusion currents, but this means that in viscous hydrodynamics you have a deviation of the distribution function from local momentum isotropy. That was a very, very good question. All right, so just assuming local momentum anisotropy, I get this decomposition here. And it's unique. Yeah? So that's the form, the most general form that J mu and T mu nu can take if the distribution function is locally isotropic. And note, I did not use exponential dependence on this variable. I only used the isotropy. And this means that the form of the energy momentum tensor is this ideal fluid decomposition, even if the system is not in local thermal equilibrium. The only thing that you need it has to be locally momentum anisotropic. And so that when you go back to what I said earlier, that in the pre-equilibrium stage, the approach to equilibrium happens in two steps. The first step is local isotropization, and the second step is thermalization. We can use this after we have reached the stage of local isotropization. And then we can discuss the approach to thermal equilibrium actually using equations that look like ideal fluid equations. If the distribution function is not exponential, where do you see that? You see that in the equation of state. There is a relationship between the pressure and the energy density, which is called the equation of state. And this equation of state is different if the system is in local thermal equilibrium than if it is not. And so if you have a locally isotropic but not thermalized state, it will have a non-thermal contribution to the pressure, and the equation of state will change, and you have to put that into the equation of state. But you can still treat these equations here. You can still use these equations, you just have to change that parameter. You also don't need chemical equilibrium, so the mu does not have to be in chemical equilibrium. What you find here is that if you don't have chemical equilibrium, the current is not conserved. So if you have, for example, a system that is oversaturated with gluons, the gluon number is not conserved. So you find that the divergence of J mu gluon is not zero. The gluons will start to fuse and reduce their number until they have reached chemical equilibrium. But you can account for that by putting here into this distribution function a non-zero value for the chemical potential. So you don't need thermal equilibrium, you don't need chemical equilibrium for this decomposition to hold. And that's important. All right. So now let me leave that up there. Any system of, so if the system is, right, so any system that, any system in nature we know has to conserve energy momentum. And this is reflected by the fact that the energy momentum tensor is free of a divergence, is divergence free. So this equation that I wrote here is a microscopic representation of the law of energy momentum conservation. Now, we also have baryon number conservation. So this is reflected by d mu j mu b is equal to 0. So note, this doesn't say that each one of the currents j mu I is conserved. It only says that this particular combination of quark minus anti-quark current is conserved. So d mu j mu I does not necessarily have to be equal to 0. So d mu j mu I can be non-zero as long as the difference between quark and anti-quark currents has zero divergence. Now, if I plug this decomposition here into these equations, I can do the following trick, and I need a little bit more space here. It's not a trick, actually. It's a nice way of organizing the calculation and think about it. What you can do is you can decompose any partial derivative d mu into, by writing it as g mu nu minus u mu plus u mu times d nu. Yeah, so I have smuggled in minus u mu, cancel it out again. So I can write this. This here is the spatial projector, delta mu nu times d nu plus u nu times d nu. And then I call this here delta mu, and I call this here d, or d by d tau, where this would be the true proper time, not just the longitudinal proper time. And so in other words, in the local rest frame, this is 1 and this is 0. So in the local rest frame, this is the time derivative in the local rest frame. And this here are the spatial gradients in the local rest frame. Yeah. So delta mu is the spatial gradient in the local rest frame. And d, which is u mu d mu, is the time derivative So this here is a way of writing the gradient in the local rest frame as a 4-vector in an arbitrary frame. And this here is a way of writing the time derivative in the local rest frame as a 4-vector in an arbitrary frame. And so I can separate a gradient in an arbitrary frame, a derivative in an arbitrary frame, into its components that correspond to spatial gradients locally and to time gradients locally. And so when you use that and plug this decomposition into these equations, and then you do this to the d mu everywhere, then you get the so plug the ideal fluid decomposition into the conservation laws. Then you get the following equations. You get n baryon dot, the time derivative of the baryon density in the local rest frame is minus n baryon times the expansion rate. You get epsilon dot, the time derivative of the energy density in the local rest frame is minus epsilon plus p times the expansion rate. And you find for the time derivative of the flow velocity, so that's the flow acceleration, you find the spatial gradient of the pressure in the local rest frame over epsilon plus p, it's the same p here, which you can write as cs squared times 1 plus cs squared times the gradient of the energy density over the energy density if P has the form cs squared times E. So this is called a simple polytropic equation of state, where you can write the pressure as a multiple of the energy density, and then that prefactor by thermodynamic identities is nothing but the speed of sound waves in that medium. So for an ideal radiation gas of massless particles, you know that the pressure is related to the energy density by a factor 1/3. The pressure is 1/3 of the energy density for an ideal gas, and that means for an ideal massless gas, that means in an ideal massless gas, the speed of sound is the square root of 1/3, which is about 0.57, a little bit more than half the speed of light. So if you have such an equation of state, then you can plug it here, and then you can figure out, pull out that factor of the sound velocity. Okay, let's look at these equations and interpret them. So what does this equation say? This equation says that if I go into the local rest frame, into a local cell, then the only way the baryon density in that cell can decrease or increase, if the fluid at that point is expanding, then it decreases, or it's contracting, then it's increasing. Yeah, so theta takes into account the change of volume locally, and because it's a conserved current, the only way the density can decrease or increase is by the volume increasing or decreasing in compensation for that. That's what this equation says. This equation says that for the energy density, it's not quite the same. If I go to the local rest frame, for the energy density to decrease, I need, again, for the fluid to expand locally. For it to increase, the fluid has to contract locally. But then the rate is not just proportional to the energy density, but there is an additional term here coming from the pressure. And that pressure accounts for the fact that as the system expands, if you have pressure in the system, that pressure does work on the surface of that little fluid cell. And that work converts thermal motion energy, local random motion energy, into collective motion energy. And so it takes out energy from the thermal energy density and puts it into collective motion. And that means that the rate of energy density is actually faster than you would expect without that work acting. If you just had the expansion by volume, it would go down like minus epsilon times theta, but because of the additional work, the energy density actually drops faster than this. So if I look at a function of time in the local rest frame, let's do proper time, and I look at n and epsilon, nb and epsilon, and I do that on a log scale, a log in a log plot, then if I just have one-dimensional pure Kane expansion, as I have initially, then the expansion rate theta, so for pure Kane expansion, theta is 1 over tau. And that means that n goes like 1 over tau, so it's a straight line in a log-log plot with a slope of 1. So this is what n does, nb does. Now, for what the energy density does, it depends on how much pressure I have in the system. Now, if the gas were a pressureless gas, a very dilute gas without any internal pressure, then this would be 0, and then this would also fall like 1 over tau. So this would be epsilon for the case of P is 0. It would also fall like 1 over tau. On the other hand, if I take a massless ideal gas where the pressure, so for ideal massless gas, where the pressure is 1/3 epsilon, then instead of epsilon, I get 4/3 epsilon here. And then this slope goes like 1 over tau to the 4/3. So this is for the ideal massless gas. So the real pressure in the system is going to be somewhere between no pressure at all and that of an ideal massless gas. That's kind of the upper limit. And so that means in real life, the energy density will be, so this is, in real life, the energy density will fall off as a function of tau for one-dimensional pure Kane expansion, somewhere between this and this behavior. And in particular, if you have viscous behavior, then it turns out that the amount of work that you do from pressure is reduced and you fall in between. Yeah? So this is kind of the range between no interactions at all and infinitely strong interactions. That's the range that you can cover here between these two guys. So that's what this second equation says. Now, what does this last equation say? This last equation is nothing but Newton's second law. Newton's second law that says that the acceleration is the force divided by the inertia. The gradient of a pressure is the hydrodynamic force. So in hydrodynamics, the gradient of the pressure is the force. And I mean, by the gradient, I mean the gradient in the local rest frame. So if in the local rest frame the pressure changes in certain directions, that gradient drives expansion. And the inertia is not just the energy density, but it's the heat function, the heat enthalpy. It's the sum of energy density and pressure. This is a special relativistic effect, or even you see it even more strongly in general relativity, that pressure is itself a form of inertia, and when you take the total inertia of the system, you have to add the pressure to the energy density. And if you have such a relationship between the pressure and the energy density as here, then you see that you can pull out the gradient of the energy density over the energy density as a normalized gradient. So the absolute value of the energy density doesn't matter here anymore. It's only the normalized gradient that matters. And this factor tells you how strongly a normalized gradient in the energy density or in the pressure, you can, of course, multiply both numerator and denominator by this constant, then you get the pressure gradient over the pressure. So how a normalized pressure gradient, how the fluid responds to a normalized pressure gradient in terms of acceleration. And what you see is if Cs squared is large, you get a lot of acceleration out of a gradient, and if Cs squared becomes small, you get very little acceleration out of a gradient. Small Cs squared is called a soft equation of state, squishy equation of state. You can have a lot of gradients and the fluid doesn't react to that. And in the limit of a phase transition, a first order phase transition, such as the liquid gas phase transition, At that point, the fluid becomes completely squishable, because any pressure inhomogeneity you can absorb by just converting gas into liquid or the other way around. So at the liquid-gas phase transition, the speed of sound is actually 0. You cannot propagate sound through a glass of boiling water, because sound is a pressure wave, and pressure inhomogeneities just convert liquid to gas or vice versa, so the sound gets completely attenuated at 0 distance. So that's the limit of 0 speed of sound. No sound propagation at all, no acceleration. So if you are in the middle of a first order phase transition, pressure gradients don't lead to acceleration. If you are not in a phase transition, but somewhere in the ideal gas limit, then you get a lot of bang for the buck. You get a large factor here. And so that's why this factor here is called the stiffness of the equation of state. And the stiff equation, so this is the stiffness factor. And a stiff equation of state, pressure gradient with a lot of acceleration, and a soft equation of state leads to any gradient with a weak acceleration. And in a phase transition, you have extreme limit of softness and you have no acceleration at all. Okay. Let's see. Any questions here? And let me see whether I said anything that I wanted to say. Everything that I wanted to say, I think. All right. So now let's go to away from the limit where the Knudsen number is basically 0, which is the ideal fluid limit, to the limit to the case where the Knudsen number is not 0, but it's still small, so that we can do perturbation of ideal fluid dynamics. So these equations here, I will leave. These equations will still play a role. So this will be 2 viscous fluid dynamics. And there are different variations. Navier-Stokes theory, called NS. Israel-Stewart theory, called IS. There is the Denikol, Nemi, Molnar, Rischke theory, DNMR, or I could call it the Frankfurt theory, which is a modern version of Israel-Stewart theory with a lot of improvements. And all 3 of these I just call viscous hydro, V-hydro. So viscous hydro is any one of these. So what's the starting point here? Well, here the starting point is that actually the distribution function is not locally isotropic. So if I want to write it in this form, starting with this form that I wrote down before, I have to allow for deviations from that behavior. But the deviation delta F from local isotropy is in some sense small, so that the Knudsen number is small. So you can identify 0 Knudsen number with delta F equals 0, and non-zero Knudsen number with delta F not equal to 0, and small Knudsen number with a small delta F when normalized to F0, to F isotropic. So for the further derivation, you can actually, you don't have to assume that the isotropic distribution is a thermal equilibrium distribution. So you don't have to assume that the dependence on this variable is exponential. But when you look into the literature, almost everybody assumes that. And so I'm also going to assume that. But I emphasize that you don't have to. And you can generalize even those formulations that are up there on the board, you can generalize them in the future by giving up on the exponential dependence of the isotropic, and then by maybe in this way making the delta F even smaller by accounting for deviations from exponential behavior already at this level without giving up isotropy. So I'm going now, okay, so remember we had T mu nu is P mu P nu, and we had J mu is the expectation value of P mu. In order to separate the components of P mu that are energy-like in the local rest frame from the ones that are spatial in the local rest frame, I play the same trick that I played here. Am I doing something wrong with this mic that it keeps... I don't... Should I just turn it off? Plane mode? Okay, that I can do. Airplane mode, yes. Flight mode, okay. Yes, let me fly here. Let's go flying. All right, so I'm going to write this as delta mu nu p nu plus u mu u nu p u mu u nu p nu. So this here I call p mu. So P with a sharp parenthesis around its Lorentz index means that it's projected in such a way that when you go to the local rest frame, it has only spatial components, no time component left over. And this here is U dot P, and that I call E. That's the energy in the local rest frame. So when you see an E, I don't want to put the LRF all the time on there. When I write an E, it always means that it's the energy in the local rest frame. So we have E times U mu. So so what this does, it decomposes P mu in some arbitrary frame into a part that is energy in the local rest frame. That's the part that points parallel to U mu. And a part that is spatial momentum in the local rest frame that points perpendicular to U mu in the arbitrary frame. So in this way we can write the particle density as the expectation value of U dot P or E, and we can write the energy density epsilon as the expectation value of U dot P squared. All right, so you give me a distribution function f of x and p, and I will write it like this and separate it into a locally isotropic part and a delta f part. And when I start trying to do that, I will immediately realize that there is an infinite way of doing that. So you have to somehow have a guiding principle that tells you how to do that. And the reason why I have an infinite way of doing that is because I have two free parameters to play with, mu and t, and those parameters I have to fix. And that is done by Landau matching. So Landau matching makes the decomposition unique by fixing the parameters t of x and mu of x in an optimal fashion. What do I mean by that? Well, what I mean by that is the following. I demand that when I write down these equations, that actually all of the contribution to the local particle density and all of the contribution to the local energy density is already contained in here. So I adjust my temperature and my chemical potential in such a way that delta F doesn't contribute anything to the particle density and anything to the energy density. The temperature is the Lagrange multiplier that I adjust so that the energy density of the system is reproduced. And the chemical potential is the Lagrange multiplier that I adjust that the particle density of the system is correctly reproduced. So optimally by requiring that the expectation that the contribution of delta F when so this is the integral over P of U dot P, which is E with delta F, that this is 0, and that the expectation value of E squared with delta F is also 0. So this second equation means delta F makes no contributions to the energy density, and this first equality means that delta F makes no contribution to the particle density. So this is how I fix mu and T, and this is how I make this separation unique. So now I have a unique decomposition. So now if you take this distribution and plug it into these definitions of the energy momentum tensor, and you write F as F iso plus delta F, so you get two contributions to the expectation values. So inserting this decomposition into the kinetic definition of J mu and T mu nu, you get the following result. You find that now J mu has a form that looks like the ideal fluid form. So this is, remember, just n times u mu plus an additional term, and that would be the a local particle number, even in the a non-zero local particle number, even in the rest frame, and we would call that a diffusion current or a heat current. That's what you were looking for. Yeah? And this V mu gets by definition no contribution from this part of the distribution. Its entire contribution comes from the delta F. So this is P. It's actually by construction perpendicular to the flow velocity because of this decomposition here and because of the matching condition. And so and it gets contribution only from delta. Then when you write the energy momentum tensor, you find from the isotropic contribution, you find the contributions that you had before. You get epsilon times u mu u nu minus p times delta mu nu. But then you find that you get another term here. You get another term that goes with delta mu nu, and you get another term here. You call this here is called the bulk. So this is called the heat conduction vector or heat conduction current. This is called the bulk viscous pressure. And this is called the shear stress or shear viscous pressure tensor, shear stress. And in this case, where pi, so all of these additional terms come from the delta F. The terms epsilon and p, they come from the isotropic part. The additional terms come from the delta F. And so the pi is actually minus 1/3 times the expectation value of p alpha with the distribution function delta. So these sharp angle brackets tell you that this is just in the local rest frame, this is just the p vector squared. So you get minus 1/3 times the expectation value of p vector squared, which is the definition of pressure, but only with the delta F contribution. So the delta F contribution to the pressure is the bulk viscous pressure. And then you have pi mu nu, and pi mu nu is the expectation value of p mu p nu in the with the delta f, where this here is the following. So p mu p nu is something that I obtain from p alpha p beta by projecting with a double projector or spin 2 projector delta mu nu alpha beta that I write up here. Delta mu nu alpha beta. Let me write and then explain it. So it gives you delta mu alpha delta mu beta plus delta mu alpha delta mu beta. So this is symmetrized between alpha and beta. I divide it by 2 minus 1/3 times delta mu nu delta alpha beta. And the physical interpretation of that projector is that this here projects the spatial components out of that in the local rest frame, and this here takes out any trace. And that means there is no, this thing has no trace. And let me put it here. So pi mu mu has no trace, pi mu mu is 0. This projector here makes sure that it's perpendicular to the flow. So it's in the local rest frame, it has only spatial components. There is no, in the local rest frame, there is no components of pi with a 0. There is no pi 0, 0, no pi 0 I, no pi I 0, only pi ij's. And so that's what this projector does. It takes out the trace. The trace part goes into this part, and it takes out the terms that are pointing in direction of mu nu, because they have been taken care of already by the ideal fluid parts. So when you allow for deviations from local isotropy, you pick up additional terms in the energy momentum tensor. You pick up this bulk viscous pressure, that's one scalar component. You pick up that shear stress, that is a symmetric tensor which has 10 components, -1 for the missing trace, which leaves 9, -4 for these 4 orthogonality conditions, which leaves 5. So I have 1 from here plus 5 from here gives me 6. And then I have 3 components from here, 3 because it's perpendicular to the flow vector. So I have 9 additional components in my energy momentum tensor and in the current, 3 here and 6 here. And I still have only these conservation laws. So these conservation laws were just enough to write down equations of motion for n, E, and P was given by the equation of state and the flow velocity. But now I have 9 additional degrees of freedom, and so far I have no additional equations. So why is that, and how do I deal with that? Well, first we have to understand, why is there a delta F? Okay, that I can still do. Let's start from a local equilibrium distribution function. And let's take Boltzmann approximation. So don't worry about Bose-Einstein or Fermi-Dirac statistics. We know local equilibrium distribution is an exponential distribution, e to the minus energy over t. Where e is the local rest frame energy. So let's take a system that is in that distribution locally, but it has an edge. So we have a temperature all the way to here, and then we have vacuum outside. What will happen? You have a pressure gradient. There's pressure inside that region, there is zero pressure outside, so there's a pressure gradient pushing it out. So the system will start to expand. Because it expands, it will cool down. So what is that slope here? That's the temperature. So if it cools down, the temperature has to go down, and that means the new distribution that the system would like to go at in these cells near the edge would be a distribution that is steeper, that corresponds to a lower temperature. So this would be e to the minus e over T2, where T2 is less than T1. So how do I get from here to there? Well, I have to take all these particles that are distributed like that and have to let them scatter with each other so that they move over from high energy to lower energy. This requires collisions. So this will take some time. You don't do that instantaneously. Collisions take some time. And the Boltzmann equation, the relaxation time in the collision term of the Boltzmann equation, gives you an estimate for that kind of time. It's given by the microscopic cross-sections. You see that the higher energy particles have to move farther than the lower energy particles because of the characteristic of that form. And so that means that reaching the new state, which will be will have a different degree of difficulty for low energy particles and for high energy particles. For high energy particles, you probably need more collisions until you get to the new equilibrium state than the lower energy particles. So after a small finite time, what will happen is that this may have moved partially like that. And that means that your distribution function is no longer an equilibrium distribution. The distribution function will have a delta f. So this is how the delta f arises. The delta f arises because the system is trying to adjust to its new equilibrium configuration, but it can't do so instantaneously, and this results in a delta f. This delta f will be very small if the collision cross-sections are huge and you have lots and lots of collisions. Then it will move over there very quickly. This delta f will be large for the same expansion rate if the cross-sections are not as big, if the system is more weakly coupled. So the delta f will be a measure of the strength of the coupling of the system. For strongly coupled systems, the delta f will be small. For weakly coupled systems, the delta f will build up and become large rather quickly. The entire approach here is prejudiced on the assumption that delta f will never become very big. So it is prejudiced on the system to be sufficiently strongly coupled that the delta f can remain small, but we cannot assume that it's zero. We'll have to account for it being non-zero. So this is where the delta f comes from. It comes from the reaction of the system to expansion and to cooling, and the reason and the fact that this doesn't happen instantaneously. Let me see whether this is a good place to break or whether I should first. Yeah, I think I would like to just end by telling you what happens when I take this decomposition here and this decomposition here and plug it into the conservation laws that I just erased. And so from d mu, j mu, b is equal to 0, and d mu, t mu nu is equal to 0, I now get the following set of equations. I get n b dot is minus n times theta plus minus the divergence of v. I get epsilon dot is minus epsilon plus p plus pi times theta plus pi mu nu sigma mu nu, and I get u dot nu is, well, I get epsilon plus pi plus p times u dot nu is the gradient of p plus pi minus delta mu nu nabla sigma pi nu sigma plus pi mu nu u dot nu. So I get my hydrodynamic equations are modified. My reduction of the baryon density now gets an additional contribution from the divergence of the number diffusion current. My energy density reduction gets an additional contribution by work done by the bulk viscous pressure, and an additional term coming from the shear stress, and that shear stress goes with sigma mu nu, which I didn't define yet, but sigma mu nu is the non-diagonal components of the velocity gradients. So it's you get that by taking derivatives of the flow velocity in different directions. You symmetrize and make it orthogonal by that double projector that I put there on the top of the board. And this is sensitive to, for example, in heavy ion collisions, I told you that initially all the expansion velocity is in the z direction and nothing happens in the transverse direction initially. So there is a large difference in the expansion rate this way and that way. That's called shear, velocity shear, and this quantity measures it. If you put mu equals z and nu equals one of the transverse directions, it would measure exactly that difference in the expansion rates in the longitudinal and transverse directions. So you see that this couples to the shear pressure and also reduces the energy density. And then in the acceleration equation, you see that the hydrodynamic force and the inertia gets an additional contribution from the bulk pressure. And then there are additional terms here on the right-hand side. And look in particular at this last term. This last term says that the acceleration is actually not purely, sorry, that index sits wrong. That index sits here. So this says that the acceleration is actually not purely in the direction of the gradient of the pressure, but there is a deflection of the acceleration coming from the shear stress. So in a system that has shear stress, the acceleration doesn't just follow the pressure gradient, it gets deflected by the fact that you have different expansion rates in different directions. So this makes things rather complicated. So same number of equations as before, but we still have this and this and this here as additional sources on the right-hand side for which we don't have an equation of motion. And for that, we have to understand this behavior here, this microscopic behavior, and the delta F that results from that from the microscopic approach. So we need an additional set of equations for these viscous, for these dissipative flows. These are called dissipative flows, and for that we have to go back to Boltzmann equation. I have to solve the Boltzmann equation in some kind of approximation. Without the microscopic dynamics, we cannot understand how these things evolve, and we'll have to do that on Thursday. Questions? Yeah. Yeah. Right. So if you have more than one species, you have this is a combination of quarks and antiquarks. So you would have to look at the equations for the quarks and for the antiquarks separately, and then you can actually have additional terms here that describe how far they are out of chemical equilibrium. So you need then you get all right. How to say that? In chemical equilibrium, there is a well-defined ratio of quarks and antiquarks to gluons. It's given by the baryon chemical potential and the temperature. If the system is out of equilibrium, the quarks and antiquarks have a non-equilibrium chemical potential, and that non-equilibrium chemical potential will turn up as an additional contribution to that vector if you look at the quark and the antiquark separately. So, yes, it's... Mm-hmm. No, you cannot in general assume the Dame deviation, because how this motion happens for quarks and how it happens for antiquarks and how it happens for gluons depends on their individual cross sections. So you can have delta Fs of different sizes for the quarks and for the gluons. That's a good question. Yeah, so it's Yeah. So I only write it down for one component, but you really have to do it for every component separately. Should I press stop? Yeah, no, I